And I'm still waiting for screen sharing to be enabled. And I can confirm to everyone this did work yesterday in rehearsals, so we have the technology. Thank you very much, Professor Iwamura. Well, good morning to everybody at Xiamen University, and good day to everyone else listening to this conference, wherever you happen to be in the world. I would like to begin by thanking the conference chair, Professor Tian, and the conference vice chairs, Professors Shi, Zhu, and Zhang, for this invitation to speak to you all today. I would also like to thank the International Advisory Committee and the local organizing committee to making this all possible. I can certainly confirm the great efforts that the local organizing committee worked to make sure that all the speakers were very well prepared for this virtual format. And I would like to thank Professors Iwamura and Zhang for chairing this session. This has been a privilege that I personally have been looking forward to speaking at this conference. And finally, I'd like to offer a hearty congratulations to Xiamen University for their 100th anniversary. Not only is Xiamen University one of China's leading universities, it also has a reputation for international collaboration and outreach, and they are an ideal host for this 23rd International Conference on Condensed Matter Nuclear Science. And as much as I would like to be with you all at Xiamen University, I'm actually very grateful that this particular meeting is being held in a virtual format because it allows me to be in two places at the same time. It allows me to be on a long-planned family vacation with my family in Hawaii. So this is a real background that you see. And yet also allows me to spend the next 3 days with you and participating in this conference series that has been so influential in my own career. And so with that, allow me to proceed with our presentation. It's really a brief introduction and 3 sections. And then I think we have time for a couple of questions afterwards. So as a longtime observer of cold fusion, I asked the question of myself and a few colleagues, what would happen if we brought well-qualified, open-minded, mid-career academic scientists together and gave them an opportunity to investigate cold fusion for a few years in an environment of privacy and some resources to do the caliber of work that they expect of themselves? Well, I'm very happy to report that we now have an answer to this question, and it's those academic scientists would recruit extraordinary graduate students, wonderful postdoctoral fellows who would spend thousands of hours designing apparatus and running cold fusion experiments, publishing their work, and then actually aspiring to do so at the highest levels of scientific impact and really publish this in Nature. So the summary is these scientists, all of whom are in the middle of their careers, were extremely proud of the work that they had done on cold fusion, and we're happy to tell the world about that. And so I stand here really representing the work not only of Google, but of 4 other great institutions: the University of British Columbia, the Massachusetts Institute of Technology, the University of Maryland, and the Lawrence Berkeley National Laboratory. And this list of 26 names here represents the people that actually made our program happen, and that informed our perspective. So they are the wonderful young researchers that did the bulk of the work, and they are also our executives at Google that provide the sponsorship. So this is really an excellent collaboration of a group of people that was more than 30 at its peak. And this is an illustration of some of these people. I'm particularly proud of this photo in front of MIT's iconic Great Dome. MIT is my alma mater, and I was very pleased for one of our quarterly meetings to be able to bring most of our research team together at MIT to discuss the progress they were all making on their own experiments. But what I most like about this photo is actually the genuine smiles on everybody's face in this photo. We had a lot of fun working on this project. So not only did we learn a lot on this exploration, but we had fun doing so. And everyone who worked on this project began by thinking they were taking some career risk by engaging on the topic of cold fusion. But by the middle of it, they realized that there was really good science to do in this parameter space, and they were getting their work published, and they were graduating with their PhDs. And when they graduated, they were getting jobs in industry and academia. And so pretty much everyone we worked with actually saw an advance in their career as a result of cold fusion. So this is all like very, very good. Now, after we published the perspective 2 years ago in May, we really didn't have an opportunity to talk about it very much. I got very busy working on Google's quantum computing project, in addition to stewarding our research in nuclear fusion. But really, this period of time went by where we didn't have much to say about it. So I welcome this opportunity to share a little bit more about our program for the first time. We actually named our program Project Charleston because Charleston is the name of the road near Google's headquarters in Mountain View, California, where we first convened in April of 2015 to start deciding what a research program to read about cold fusion might look like. And you might ask, what does Google have to be interested in about cold fusion? Well, the reality is that my colleagues, Ross Koenigstein, who you see pictured on the left, and David Fork, who you see pictured on the right, were part of a 5-year effort in Google research called RE less than C, renewable energy is cheaper than coal. And so for 5 years, a team at Google really assessed the potential of renewable energies. And they came to an inconvenient conclusion, which is to really kick the entire habit of fossil fuels. We need a more transformative energy technology than the renewable energy technologies that are being commercialized today. So that had seeded in Google's mind the idea to maybe do something different. Now, as for myself, I have been interested in cold fusion for more than 20 years, and I must confess, this is my 9th International Conference on Condensed Matter and Nuclear Science. My first conference was actually ICCF-10 held in Cambridge, Massachusetts, under the chairmanship of Peter Hagelstein. And it was there that I got to meet Martin Fleischmann, the icon of our field. A couple of years later, in Marseille, France, under the chairmanship of Jean-Paul Bibirien, I got to meet one of my intellectual heroes, Brian Josephson. And for those of you that don't know, Josephson junctions are the underlying technology behind Google's gate-based superconducting quantum computers, the technology that I spend most of my time working on today. And then I followed the field continuously since then. So that is the perspective I bring to this partnership. And Ross, Dave, and I really joined forces in 2015 with Google's sponsorship to address the points made on this slide. So our motivation was quite simple. Given the enormous benefits that cold fusion could bring to our society, it is just unconscionable that there remains this unsettled status about it. Is it real? Is it not real? Is it ready for commercialization? Is it still basic science? But we thought perhaps we could help bring some credible current research, publish that work, and that could help inform this debate so that young researchers choosing to maybe establish a career in LENR research would have that information available to help them decide. And funding agencies, whether private or public, could also lean on that research to decide whether or not programs like this should be funded. Our goal was straightforward, and it's been a long-time ambition of the LENR community to have a reference experiment, and we adopted that goal. And we wanted an experiment that could be reasonably reproduced by people skilled in the art a reasonable number of times. And once you have a reference experiment that can be studied, understood, and improved upon, then you have the basis for a science and ultimately a technology. So that is and remains our goal. We also thought it was essential to recruit new scientists to the field. And these are some of the criteria we were looking for in those new scientists. So most obviously, they had to be experts in fields relevant to cold fusion. But importantly to us, they had to have no prior position on cold fusion, for or against. We wanted them to be objective on the topic, so we screened for that. They had to be willing to collaborate as a peer group amongst themselves and with Google to form the first line of peer review on any work that was done. And they had to commit to publish what was learned so there could be a record of this collective effort that we went through. Here are some statistics about our program. We actually conducted this as a portfolio of sponsored research. We ended up having 8 new academic groups working with us. And we worked with 8 experienced LENR researchers or groups. So there were 16 active collaborations that were in our portfolio. We attempted in earnest to collaborate 6 more times, but those attempts were unsuccessful. Usually, the scientists were very willing to collaborate with us, but their financial sponsors were not. I'm going to talk more about that later. We evaluated 12 calorimeter designs throughout our program. So while calorimetry is tricky, it is not intractable. And we believe we gained the experience to know that we could detect excess heat if we saw it. And finally, I wanted to reinforce that no laboratory work was conducted at Google. This was a program of externally sponsored research. We ended up investing about $10 million in that external sponsored research, and the collaborations varied in duration and funding amounts, and they started and stopped at different times. So as we learned more, we took on other collaborations. The results of this work have yielded 27 peer-reviewed articles to date. That includes 6 Nature family papers and 2 granted US patents. So the notion that you cannot get papers published in high-impact journals or granted US patents is not an accurate one. Our experience was to the contrary. And in fact, the editors of the journals we worked with, proved to be very receptive to our work. And I want to thank my colleagues at the University of British Columbia. They have actually publicly posted this list of articles to date. The link is posted there. I'm sure the organizers of this conference will make that link available. And we will aspire to keep that list current so that you can continue to see the publications as they emerge. This is a chart that I found particularly interesting. In the blue bars indicate the funding, so the input of scientific research. The orange bars indicate the output or the publications over time. And what this shows to me is that you need to run a cold fusion research program for a minimum of 5 years for it really to bear fruit. Because had we only run the program for 3 years in 2015, 2016, and 2017, we might have only had a few publications result from this. But because we were able to keep it going for the full 5-year duration, we were able to see those publications work their way through peer review and ultimately have the impact we hope for them to have. Now, I don't want to presume that everyone listening into this conference today has read our Nature perspective or even knows much about what we're talking about. So I want to spend this next section just summarizing our perspective briefly in a few slides. So there were 3 authors from Google, and we really provided some program management and some technical management and coherence to the program. But our principal investigators are the 4 people you see listed here. They're Curtis Berlinguet, our chemist, Yetmin Chang, our materials scientist, Jeremy Monday and Thomas Schenkel, our physicists, and they've led research efforts at the University of British Columbia, MIT, the University of Maryland, and the Lawrence Berkeley National Laboratory. And you can see from their other credentials on this slide, they have terrific academic training. They're very entrepreneurial. There are many startups, companies started by this group of people. And these turned out to be wonderful principal investigators and ended up being our co-authors on the Nature perspective. I want to assure everyone this was not a paper study. We built apparatus, we broke apparatus, we built it again in an improved format. We ran a lot of experiments. This photo montage is intended to give you a flavor for some of that. In the limited space afforded by a Nature perspective, we didn't have an opportunity to tell our entire narrative, and that would have been a very long narrative. But we did focus on our testing of 3 foundational claims of the cold fusion community. And I'm going to briefly describe those 3 claims that we tested here. So the first claim that we tested is the notion that you need to load a metal cathode with an extraordinary high degree of hydrogen or deuterium, we use those terms interchangeably here, in order to establish the conditions under which cold fusion is hypothesized to exist. And I recognize there's a debate whether it's the loading per se or some other secondary effects caused by the loading, but nevertheless, a high degree of loading seems to be at the core of many cold fusion claims. We credit Mike McCrubre and his team at SRI for quantifying the level of loading required as 0.875 atoms of hydrogen per palladium atoms as the necessary threshold. So our experience, as we show here, is that it is both very difficult to make highly hydrided materials, and it's very difficult to measure the hydrogen loading in those materials. Now, the situation why they're difficult to make is because we're essentially dealing with a leaky bucket. There's a very dynamic equilibrium between getting hydrogen into the metal sample and that hydrogen wanting to leave the metal sample. And so what you have is that the loadings realized end up being well short of the thermodynamic limit. But it's not impossible. We were able to achieve an exceptionally high loading of 0.96, but we were able to do it only once. Now, what I want to note is, look at those error bars on that. Using the technique of in situ X-ray diffraction, which measures the lattice expansion as hydrogen enters it, we're able to get a very accurate measurement of the loading. So our conclusion for this claim is that a lot more work is required in order to make many samples of highly loaded hydrides to comprehensively, evaluate the thermodynamic claims. So more work to do on this claim. The second claim we sought to evaluate was the claim that certain metal powders, particularly nickel and lithium aluminum hydride, produce excess heat when heated in hydrogen gas. Now you have to remember that in 2015 and 2016, this was a very fashionable topic in our community because there were claims that you could get excess heat by heating up these powders. So to test these claims, we designed a calorimeter that was capable of operating at 1,200 degrees Celsius and 33 atmospheres of pressure with less than 2% measurement uncertainty. You see some of those calorimeters pictured here. Now, our experimental objective was to be able to detect excess heat events in excess of 10% with a 98% confidence level. And in order to do that, we had to run each experiment in parallel 4 times. So what you see here is our experimental apparatus, and every week we would run a new experiment. We would calibrate each calorimeter before the experimental run. We would then conduct the experimental run, and then we would calibrate those calorimeters again after the run. And so each experiment took 1 week. So over the course of 16 months, we were able to evaluate more than 100 variables of temperature, pressure, sample composition, particle size, and surface treatment. So using what was published in the literature, we evaluate a subset of the available parameter space. And in our experience, we did not detect an excess heat event once in testing 420 samples. Now, we fully concede that the experimental parameter space is vast, and we may not have covered the portion of it that does lead to excess heat. And to aid anyone else that wants to further this research, we have published our calorimeter designs and our calibration protocols so that anyone who wants to benefit from them can. The third claim we sought to evaluate was that nuclear byproducts, in particular tritium, can be generated in low energy pulse plasma experiments. And this was really to evaluate the work done of Thomas Claytor and his colleagues in the mid-1990s at Los Alamos National Laboratories in the United States. And so using another US national laboratory, the Lawrence Berkeley National Laboratory, we built a pulse plasma apparatus that had a stainless steel cage, a palladium wire target, and we housed that in a deuterium gas environment where we control the pressure. And then when we applied the electrical current, we were able to ionize the deuterium gas and have those deuterium ions, the deuterons, impinge on the palladium wire cathode, as the target. And we ran these experiments for hours to weeks, many times, but we were never able to detect the tritium signal above background. But this experiment also requires a lot more work to fully flesh out. What we essentially learned from our initial runs is that we needed to redesign the apparatus in order to allow us to more accurately measure the reaction rates of fusion below 2 kiloelectron volts. And when we looked at the available data, for reaction rates below 2 keV, first of all, the data is very sparse. And secondly, the data that's available has very large error bars. And so any attempt to improve that situation, we think is very worthwhile. So we're enthused to continue this work. The other very interesting thing is that these very low energies, fusion rate enhancement mechanisms, such as electron screening, start to become very significant. So we think there's a lot of interesting science to do here that can inform low energy nuclear reaction physics in general. So stepping back at our perspective, what are the key takeaways? So first, did we find a reference experiment? The answer is no, but we still believe this remains a very worthy pursuit. However, did we find that cold fusion research was compatible with mainstream academic practice? The answer is yes. It turns out that the incentives and the interests of researchers and sponsors can and must be aligned for this to make progress. And the most important way to align those actually is committing to publish in high impact peer reviewed journals. If you set that standard as the bar for your work, knowing that you're going to have to tell your peers what you did from the outset, it establishes like a very motivating tone to the research effort. And so that's what we did, and we believe we've been somewhat successful. So 2 more sections here quickly. Let me start by just reviewing what's happened in the last 2 years since we published Nature Perspective. Well, first of all, we were hit with the global pandemic. And I know the situation is non-uniform around the world, and I hope things are looking better where you are located. I can tell you from my perspective in Northern California, it really looks like we've turned a corner and people are starting to be optimistic, want to get back to work. And if I dare say, they're looking to see if science can solve other global issues, such as climate change and adaptation. So things are looking better from where we are. The other thing that's becoming very clear is both the need and the cost of transitioning to a low carbon economy. This is a report published by the International Energy Agency just last month that's showing some of the consensus forming. So the IEA estimates that we're going to have to invest $4 trillion annually by 2050 to limit the worst effects of climate change. And they define that by limiting the temperature rise up to 1.5 degrees Celsius by 2100. So if you look at over the next 30 years, that's about $100 trillion has to be invested. And whenever you see a sum of money that large, influential people start asking, are all options on the table? And I can confirm from personal experience that over the last 6 months, interest in fusion has increased dramatically. That's hot fusion, that's cold fusion, that's other ways to generate energy in a zero carbon way. The other thing I'm very happy to report is that our Nature Perspective is having its intended impact. People are reading the report. They're being inspired by the report. We're very flattered by these 2 groups that cite our report as part of their motivation to enter the field. We're very happy that both these groups seem like they're very well funded too. So perhaps the perspective is helpful to funding agencies. And we have to pinch ourselves that of all the Nature papers that have been published, our Nature Perspective ranks amongst the top 150 read in the last 2 years. So with 20,000 article accesses, people are reading our perspective. And as we thought it might happen, it's taken a couple of years for them to appreciate the messages we were trying to convey. And lastly, I want to convey that technologies based on collective quantum effects, such as quantum computing, quantum communications, and quantum sensing, are on the rise. So I work on Google's quantum computing efforts, and I'm very happy to say that it looks like there are going to be several efforts around the world. They're going to have a large-scale useful quantum computer by the end of this decade. Similar progress is being made in quantum communications. A few years ago, a Chinese group was able to beam an entangled state from the ground station to a satellite to another ground station, thereby leading the world in quantum communications. So these technologies are getting billions of dollars of support and attracting thousands of researchers. And I think we all might dare to dream that quantum energetics might add to that. So to the extent that LENR may itself be a collective quantum effect, I think there is reason to be optimistic that these other tools that exploit quantum collective effects could also give LNR research a boost. So I'd like to conclude my talk with the question that's been weighing on my mind, and I know it's weighing on many of our minds, but given what we know now, what should we do next? And I invite everyone on this call to ask themselves the same question. So collectively, given what we now know, what should we do next? Now, I want to be clear that these forward-looking statements are mine, and they are not necessarily the official position of Google, but I want to be very candid with you about kind of where my mind is. So first of all, there was a lot of reason to be optimistic in 2015. If we roll back the clock to that time, we have to give credit to Andrea Rossi and the excitement his ECAT created for our community. It seemed to be the real prospect of an LNR-powered device entering the market reasonably soon. And so we had that saga. And then we had two great philanthropists and champions for the climate and champions for technology innovation generally. Tom Darden organized a bunch of LNR researchers into industrial heat, and Bill Gates ended up sponsoring an effort at Texas Tech University that also included many of the greats in LNR research. But that wasn't all. We had the NIDO MHE project getting off the ground in Japan, and we're going to hear later today about that. Sydney Kimmel Institute for Nuclear Renaissance was in mid-swing with their work. And then in India, Current Science, one of their scientific magazines, published a special section on low-energy nuclear reactions that included 33 scientific papers. So there we were, at the start of 2015, thinking that LNR, might finally be its time. So I think we have to ask ourselves the question, so what happened? And I'll be the first to acknowledge that there is and remains a heated debate in the LNR community about the degree to which anomalous effects have already been proven. But for everyone that says they're proven, please show me and others the truly independent replications. We were not able to find them. In fact, it was our experience that the LNR community either cannot teach or will not teach, and that the failure to share the best of what is known has impeded scientific progress. Now, looking back to 2015, one may have said there were commercial reasons to keep secrets amongst ourselves. But looking from where we stand today in 2021, there is such a need for this technology, and it's my personal view that this technology is still at such a formative stage. We're still at the basic science stage. The preferred embodiments are still very many years away. If there's some way that we could come together to accelerate our rate of progress, that would be enormously beneficial. And I'm inspired by Mike McCruberry's quote that he gave at the great conference in Japan. Collectively, we have the answer. Individually, none of us does. So I'm looking forward to the rest of this conference to figuring if there are ways that we can collaborate and take advantage of the opportunities that we're presented with to really cause this field, to increase its rate of advancement. So my final slide is going to end with two messages, and it's for the two constituencies participating in this conference. So first of all, to the LNR researchers out there, I want to say what I think you all know, that there is a kind place in history for the person or group who successfully enables a truly independent replication of their claimed anomalous effects. And I would actually challenge us as a community to have the opening keynote address at ICCF-24 to be a presentation on a jointly authored peer-reviewed journal article about a set of claims and their independent replication. And my final words are a message to the new researchers who might be participating on this call. Let's invite 100 new scientists in this field. Let's support them, let's encourage them. We will learn from them. These new young scientists come with different mindsets, different tools, and different methodologies, which can be extremely helpful to our field. And I want to just quote the final phrase of the abstract in our Nature perspective. We contend that there's still much interesting science to be done in this underexplored parameter space. And so with the spirit that we don't know all there is to know, and there's still so much more to learn, I invite the existing LNR community and 100 new scientists to join us, and let's go exploring. And so with that, I thank you for your time. Professor Yamura, I hand the stage back to you, and thank you all.
Thank you. Thank you very much. time is running. We are running behind. So I would like to